Good evening, everyone. We'll start today's session, and okay. So this week was majorly dedicated to the partial differential equations, and today we'll solve some of the problems, and mostly they will clear your doubts. And if you have doubts, you can post or directly ask. Yeah. So we'll start for the today's session. So this is the first question. So I hope you can hear me. Okay. Yeah. Okay. So this question is the wave equation in 3D is given. Okay. The wave equation in 3D is given by this equation. So del square u is equal to 1/4 the second order partial derivative of u with respect to time. The velocity of the wave is okay. So we'll see how the wave equation in general. Let's say if we are talking about the 1D case, so in that case the wave equation will be of this form, and you can see that this is a C, and if you like do the dimensional analysis, then you can see that like whether this term should be C or C square. So let's say so C will have the dimension of meter or units of meter per second, and if we multiply this side, it will be meter square per second, and then right hand side will have the units of let's say u has some, let's say, random units. I will just say some random units times x square. So x square will have meter square, and if we see the term that is on the left hand side, it will also have a random unit and divided by time square. Okay, sorry, here it should be c square. Okay, one second. So s square. So if you see that this meter square and meter square will get cancelled. So C has the unit of meter per second, and you can see that the dimensionally they are matching. So this term whatever is there on this, it should be 1/c square, and we can see that c square is equal to 4, and that's how c is equal to 2. Okay, so this was like, if you know this equation, it is straightforward. Even if you don't know, you can just cross check with the dimensions, and then can directly give this answer. Okay, and yeah, so I hope this is clear. Okay, so we'll go to the next problem. Okay, the eigenvalues of the equation, this is the differential equation given, is equal to 0 r. Okay, so we have this equation given, 4d square plus 3d, and basically we are trying to solve the characteristic equation, where we'll substitute y equal to e raised to lambda, and let's say d means the operator, which is d by dx. So we'll assume that it is y equal to e raised to lambda x. So if we substitute this, so d square is the second derivative, so that time we'll get lambda square e raised to lambda x minus 4. Okay, so this is the third derivative, so lambda cube e raised to lambda x. Then second derivative of y will be e raised to lambda square e raised to lambda x plus 3 e raised to lambda x. Okay, for one derivative, first derivative. Okay, and this is equal to 0. So we can take this e raised to lambda x common, and what finally we'll get is lambda cube minus 4 lambda square plus 3 lambda is equal to 0. And let's say take lambda common, so lambda square minus 4 lambda plus 3 equal to 0. And we can write it, or we can factorize this term in the bracket, and like lambda minus 3 and lambda minus 1 equal to 0. So we can see that the roots are lambda equal to 0, lambda is equal to 1, and lambda is equal to 3. So this can be, or these are the equations that will satisfy this equation. And the 0 and 3 are already given, so the only root that is not given is 1. So this is the correct answer. Okay, so we will go to the next question. I hope this was clear. Okay, so the next question is which among these is a values. Hello. Okay, so which among these is a value specified boundary condition? So if you see these different boundary conditions, so Dirichlet boundary conditions, so let's say there is a, let's say x equal to 0 and x equal to L, and let's say we are interested in the let's say the temperature or the heat conduction equation. So in that case, let's say the temperature at this is given, let's say. So let's say the temperature at x equal to 0 is given as T0, and temperature at x equal to L is given as, let's say, TL. So this type of boundary condition is called as a Dirichlet boundary condition. And let's say there is another type of boundary condition. Let's say at x equal to 0 and x equal to L, let's say we know how much, let's say, heat flux is coming from this side. So if you see the Fourier law of heat conduction, it is, let's say, the rate of heat transfer is minus k, let's say, dt by dx. So let's say this q dot at x is equal to 0 is given. Let's say it is some q naught. So in that case, it is nothing but what is given is dt by dx. So if dt by dx is given, and let's say at this boundary also how much heat flux at this boundary condition is given, let's say ql. Okay, so these values, let's say, are specified, that corresponds to given the time derivative or the derivative of the temperature. So if that is given, that is known as Newman boundary condition. So this is Newman, and this one is Dirichlet. And if, let's say, at some at this boundary temperature is given at x equal to 0, and other boundary the heat flux is given, that time it will be the mixed boundary condition, and that is also known as Robin boundary condition. And let's say symmetric boundary condition is there in that, let's say at the center itself there is some heat source, so both the left and right hand side, let's say, are symmetric. So, or some sort of boundary conditions where it tells that at the whatever the heat transfer is there at the left, as like that goes from one end, or the temperature at left and right boundary is same. So some sort of symmetric boundary conditions are given. So that is another boundary condition. So the value specified boundary conditions are nothing but the Dirichlet boundary conditions. So this A is correct answer. Okay, so we'll go to the next question. Okay, so the next question is the complete solution of PDE. So the PDE is given, and let's say A and B are the arbitrary constant. So already options are given. So one way we can try is substitute these options and see which equation matches. And we will do that first. And once we get the answer, I will explain one more method which we can use to solve actually this type of equation. Okay, so the equation that is given is dou z by dou x plus y dou z by dou y minus z dou z by dou x and dou z by dou y. Okay, so let's say try first option where z is equal to ax plus by minus ab. Okay, so let's say dou z by dou x is equal to a, dou z by dou y is equal to b, and yeah, that's all what we need. Okay, so if we substitute these values into this equation, let's say x into a plus y into b minus z is let's say minus ax minus by plus ab is equal to so let's say this is we'll say LHS, and then we'll see what remains. These terms will get cancelled, and AB equal to LHS, and if we see the RHS is equal to A into B, so we can see that RHS equal to LHS, left hand and right hand are equal, so this satisfies the equation. Okay, so okay, we'll try one more this, and then let's say we already have the solution. I will not try C and D, that you can try later, but we'll try B whether it works or not. So the option B is x square plus y square minus 2ab. Okay, so z is equal to is given, and the equation is x dou z by dou x plus y dou z by dou y minus z dou z by dou x and dou z by dou y. Okay, so if we find out the derivative, partial derivative dou z by dou x, it will be 2x, and dou z by dou y is equal to 2y. So let's say, so this is our left hand side, and this is the right hand side. So LHS is equal to x into partial derivative of z with x is 2x plus y into dou z by dou y is 2y minus z. So we are assuming this z as the solution, so x square minus y square minus plus 2ab. Okay, so in that case x square, and here 2x square is there, so we will get remain only 1x square, then y square plus 2ab. Okay, so this is the LHS, and if we see the RHS, so RHS is nothing but this. So what we will get is 2x into 2y, which is 4xy. So this z that we assumed does not satisfy this equation whatever we have. So this is not the solution. So we already tested the first option and it is satisfying. So this is the correct answer. And we'll see one method which is actually you don't need to apply, or it is not supposed to it is not discussed in the lecture, but anyway I will just give you the method, and this is a fairly general method, and you can use it for non-linear. Even this you can see that there is a term which is non-linear on the right hand side, so this can be applied to this type of equations also. Okay, so the method name is the Charpit's method, and okay, so this so let's say what equation we have is x into dou z by dou x plus y into dou z by dou y minus z is equal to dou z by dou x dou z by dou y. Okay, so here z is nothing but the function of x and y, and if we take the partial derivative of z with respect to x, and let's call it as p, and partial derivative of z with respect to y, let's call it as q. So the whole equation we can write as x into p plus y into q minus z and p into q. Okay, so this is the equation that we have, and if we take this term on the left hand side, and so what we'll get is xp plus yq minus z minus pq equal to 0, and we can call this whole equation as f of x y z p comma q, and which is nothing but xp plus yq minus z minus pq equal to 0. So this is the equation, and it is, so you can see this term has made it complicated to solve this equation. So we so there is so this Charpit's method can be applied to like general situations. I will write what this method is. So the formula that is derived with this method is dx by fp. So fp is nothing but the partial derivative of this function with respect to p. Then next term you can guess, because x we are taking the derivative of f with respect to p. So for y that corresponding term is q, so the next obviously this will be q, and the next will be dz, and dz if you see this term, so this term you can, if we differentiate with z, it will be let's say dou z by dou x dx plus dou z by dou y dy. Okay, so similarly you can see that this terms they will combine together to form the dz. So you can see this is a p and this is q. So at the lower part it will be, we are at the top we are multiplying component rule if we use, so that is nothing but at the bottom we will get fp plus q fq. Okay, and last two terms will be related to dp and dq, and those are minus fx plus p fz and minus fy plus q fz. Okay, so you can see that p corresponds to the derivative with respect to x, so you can see that this has x derivative, and p also corresponds to x, so that has come. So I'm just telling how to you can remember this equation. So that's how this like term you can remember. And similarly you can change for the y. So instead of p, q has come here, and instead of x, y has come here, and p instead of p, q, and then z is anyway it's like symmetric or for x and y, so this term has not changed, f of z. So this is the equation, and we'll see how we can use this relation to solve this equation that is given. Okay, so this is fairly general, so you can try to solve a problem with this method. It will be like you can apply it to anywhere. Okay, so the question that is dou z by dou x plus y, or dou z by dou y minus z. Okay, so okay, I have already written then. Okay, dou z by dou x and dou z by dou y. So this is so we have already written this f. So if f is equal to xp plus yq minus z minus pq. Okay, so actually this is the equation where actually we don't need to write equations for all these like three terms. We'll just use this two terms. So it is not, so even this equation is big, so it is not always necessary that we should consider all the terms. So even depending on the equation, sometimes even so what we have to do is we have to take two terms at a time from this equation, and in this case we'll see that only this the last two terms will be sufficient to solve this equation. So I will just write this last two equations, and we'll see how what we get. So dp is equal to minus fx plus p f of z is equal to dq minus f of y plus q f of z. Okay, so dp divided by minus, so if we differentiate this f with respect to x, so we'll get p, there is nowhere else there is x, so this is fine, plus p into, if we differentiate with z, it will be minus 1 okay, and similarly we'll apply this equation to y. So if we differentiate f with respect to y, I'll get q plus q into f of z. So if we differentiate this, again this will be minus 1. Okay, so what we have is dp by 0 and dq by 0, and in general, let's say this is constants are not 0, so in regular case we can just write this is equal to k, and if we write, let's say this k, so you can see that dp is equal to okay, so dp is equal to 0 and dp is equal to 0, so we'll get p is equal to, let's say, constant on integration, and if we see here dq is equal to 0, that will give q equal to, let's say, some constant which is b. So if we substitute p and q in this equation, so so already we saw that p is nothing but dou z by dou x, and q is dou z by dou y. So if we substitute this into this equation, what we'll get is x into a plus, yeah, one second. Okay, so see if we what has happened, here is okay. Okay, so what we have is p is equal to a, and q is equal to b, and p is nothing but dou z by dou x, which is we'll use, instead of this we'll write a, and instead of q is nothing but dou z by dou y, which is b. So if we substitute these values into this equation, so what we'll get is x into a plus, instead of this we'll write b, so which is y into b minus z is equal to, so this is nothing but a, and this is will be b, so ab. So you can see that if we rearrange, we will get ax plus by minus ab. So this is the method to actually get the solution, and the whatever we tried
Sir,
before.
sorry to interrupt, sir, but
Yeah.
like I guess you have shared screen, I guess, like about, but we are not getting it. Like I'm not getting.
Okay, I will just, oh sorry. Can you see now?
Yes, sir. Now clear, sir.
Okay. So did you got this how it is solved with Charpit's method?
No, sir. The previous, the dou z by dou x is equals to a. That's the last problem which I understood. Like after this, like there was some network issue and the
Okay.
screen was not visible. I didn't get it.
Okay, so the Charpit's method is a general method to solve the equations, partial differential equation. So let's say we have this f equal to x, y, z, uh, pq equal to 0. So this is the general form of the partial differential equation, where dou z by dou x is equal to p, and dou z by dou y is equal to q. So this is the partial differential equation if we have. So we can use Charpit's method to solve it. So what this methods, so after like there is some derivation, so you can check out, but then finally what it gives is, so it gives this equation dx by the partial derivative of f with respect to p. So you can see that p is nothing but the partial derivative of z with respect to x. So you can relate this dx with what term should come below. So similarly for dy, you can see that this q corresponds to y derivative, so that's why this, so you can just remember that way. So okay, and for dz you can remember this term by considering this equation. So let's say z is nothing but the function of x and y. So you can see that z is nothing but the function of x and y. So if we take the derivative, it will be dou z by dou x dx plus dou z by dou y dy. So this is the identity, and you can see that if we take the component dou dividend dou for this, so in order to convert, take the combination of these two terms to get the third term in this expression. So you can see that dz we will get by taking by taking the combination using this equation. So similarly at the new denominator also we should take, so that's how you can think of we got this the denominator. And then for these two terms, they are related to dp and dq, and I would say you can just remember one of this term So the dp is related to f of x plus p f of z. So and then if we go to the second term, instead of x you are supposed to write y, and instead of p you are supposed to write q. So this is the Charpit equation. So you can solve some problems with this method, and then I think you will understand this method. So we'll see how we can use this method to actually solve these equations, in like instead of trying the different options, you can actually solve this equation. So what we will do is, so this is the equation, and where is dou z by dou x, we are substituting p, and dou z by dou y we are substituting q. So this is the expression we have. So f is equal to xp, so this is the first term, then yq minus z, and then the RHS we have taken on the left side, which is minus pq. And so this what is Charpit's equation is, we have to take two terms at a time to solve, and then solve that two term for this, like we have to take, let's say this, we are taking the first term and second term equality, and then we can solve it till, so it might be solvable or might not be solvable, but we can try combinations which works. So for this current method, you can see this combination will work better. So this combination we are trying now, which is the second second last term and last term. So if we take this combination, f of x we can find out from this. So we are differentiating this with respect to x, so this is the first term in the denominator, and plus p into f of z, and that is nothing but minus 1. So that's how we got the first term, and similarly we get the second term. And actually this you can see that denominator vanishes, which is 0 for both the cases, for both the terms. But in general this need not to be 0, so we can just write this both term equal to, let's say, k. But now it has happened so that the denominator is 0, so we can just write dp is equal to 0 as a limiting case, so that their limit exists. So we can say dq is equal to 0, and that is nothing but p must be some constant, so we are saying that p is equal to a, and q is equal to some constant which is b. So we got p and q, and p and q nothing but the partial derivative with respect to x and y. So we can just substitute this p and q in this equation, and that is nothing but the solution to this PD. So that's what is done. So we have just substituted the partial derivatives value here, and then this is the solution. So yeah, so that's how we applied the Charpit's method to get the solution.
Yes, sir. Understood, sir. Sir, another thing, that f of z is equals to minus 1, and how did we take that one?
Which one? F of z is?
Yes, sir. Like while we substitute, yes, sir, f of x and f of z.
F of x and this one you are saying fx?
Yes, sir.
So
yes, sir.
so we have this expression, right? So what we did is we took this term to the left, and so yeah, so this was the actual equation that is given. So we have just replaced the partial derivative with p and q, and took this term on the left. So we got this expression, and so f is nothing but we are saying this is the f. So we just wrote this f value here, and if we see here, we are taking the x derivative, we are treating this function, you can see x, y, z, p, q, they are kind of independent variables we are treating. So when we differentiate with respect to x, we can treat every other as a constant that time. So you can just differentiate this f with respect to x. So you can see that only x is here. So if you differentiate it with x, only value left is p. So that's how we got p. If you differentiate with respect to z, only z is here. So that is minus. So if we differentiate with z, it will be minus 1. So that's how this minus 1 came. Got it?
Yes, sir. Now I understood, sir.
Okay. So this is actually fairly general method. So if you find that the problem is, like, you are feeling that it is difficult to solve, you can try applying this Charpit's method and solve it. So yeah. Sometimes it is not that Charpit's method will be simple also, but you can give a try. Okay, so we'll solve the next question. Okay, so the next question is the Fourier constant a0 for the function. So this is function, and it was actually the last week question. So f of x is equal to x plus x square, and the range is minus pi to, actually the domain x or x is in this range. So a0 is nothing but 1 upon 2 pi, integration from minus pi to pi f of x dx. So we'll just integrate, and and you can see that this x is odd term, so that integration from minus pi to pi will be 0. So we'll just consider this second term. So we'll write 0 plus 1 upon 2 pi, for this is 0 for first term. Then the next term integration will be x cubed by 3, and limit will be minus pi to pi. So on such, okay, let's 1 upon 2 pi, 1 by 3, and pi cube minus minus plus pi cube, which will be 1 upon 2 pi, 1 by 3, and 2 pi cube. So a0 is nothing but 2 pi 1 upon 3, 2 into pi cube. So this 2 and 2 will get cancelled, and 1 of the pi will get cancelled. It will be pi square by 3. So this is the a0. This was the simple. So this is pi square by 3. Okay. So this is the correct answer. Okay, so the next question is the number of so this number is given and has how many significant digits. So here the thing is, like, we should count these zeros also. So 1 2 3 4 5 6 7, so there are total 7 significant digits. So this is correct. Okay, so this one was also simple question. Okay, so then next question is which of the following equations do not satisfies the PD. So what we'll do is we'll test all these options and solve it. So there is no unique solution for this wave equation. So wave equation can actually have multiple solutions. Like, uniqueness is not guaranteed, because you can see that if you, let's say this is some wave is there, and so let's say this is a right traveling wave. So what this equation tells is that this form will maintain, and it will just keep on going, let's say, on the right hand side. So let's say you can give any functional form for this. You can give any functional form, and still it will so whatever disturbance initial state you give, so that will just keep on continuing forward. So this is, let's say, t equal to 0, this is the state, and this is t equal to some, let's say, t1, this is the state. So similarly, if this is, so similarly for case 1, let's say this is at t equal to 0, and this is at t equal to t1. So this is just keep on moving. So you can see that this is the functional form is doesn't matter. So it is just keep on traveling based on, so either it can be left running, right running, so that is possible. We just the functional form can be anything, so initial condition can be anything. Based on that, these equations will get decided. So we'll see, start with the first equation, and we'll substitute and see whether it works or not. So we'll start with, let's say, option 1, which is u is equal to cos of 3x minus y. and equation is, so we'll take the its first derivative, dou u by dou x, which will be, if we differentiate with x, it will be minus sine 3x minus y, and then we have to differentiate this also, so that will be 3. Okay, so now again we'll differentiate this with respect to x. It will be minus cos 3x minus y, and 3 again will come out, so it will be 9. Okay, so this one okay, so this double derivative with respect to x we got, will differentiate. Okay, so now let's say first derivative of u with respect to y, so it will be minus sine 3x minus y, and if we differentiate with this term also, it will be minus 1. So dou square u by dou y square, then the derivative of sine will be cos, so cos 3x minus y, and again we have to differentiate this because of the chain rule that we are using, and if we write this, it will be minus cos of 3x minus y, and yeah, so you can see that this term is same as this one with minus sign. So we can write dou square, so this term itself we can write 9 into this term, which is dou square u by dou x dou y square, and which is nothing but the equation also. So this is so this works, the first equation works, so we can try the next equation. So second equation is u is equal to x square plus y square. So if you differentiate directly with x twice, you will get 2, and if you differentiate this u twice with respect to, let's say, y, which is symmetric in x and y, so it will be 2, and you can see that dou square u by dou x square is equal to dou square u by dou y square, and but that is not the equation, so here 9 is missing, so this is does not satisfy, this is not the solution. So similarly we can try for sine 3x minus y, and you can see that the inside term is same here, and you can see that this actually should satisfy, which is because of the nature of the wave equation. So if whatever function with 3x minus y is, if it is there, it should satisfy this equation. So we'll see that whether C works or not. We are expecting that C should work, because the first and third option have the same term which is inside the 3x minus y. Okay, so we'll try the third option, sine 3x minus y. Okay, so this is if you assume u to be this, so dou u by dou x will be cos 3x minus y, and we have to chain rule, we have to use this, take the derivative, it will be 3, again dou u by dou x square, so differentiating cos will be minus sine 3x minus y, and by the chain rule this will be 9. Okay, so the next term is dou square u by dou y, let's say first derivative, dou y is equal to, so if we differentiate this with respect to y, it will be cos 3x minus y, and okay, we'll have to differentiate the term in the bracket, which will be minus 1. Now differentiate this again with y, so what we'll get is the derivative of cos will be minus sine 3x minus y, and this again minus 1 square. Okay, so this is nothing but minus sine 3x minus y, and this is nothing but the term that exists here, so which is 9 dou square u by dou y square, which is nothing but the given equation, so this works. So this works, and you can see that this term actually you can try for this. But let's say if we rewrite this equation, e raised to minus 3 pi x, and let's say sine pi by y is there, sine of pi y, we can write the Euler form e raised to I pi y, and we'll say this whole term, we are interested in sine, we can say this is imaginary term from this. So what we can write here is imaginary of e raised to let's say, so let's say this 3x, we'll take minus pi out, let's say minus pi, so what we left is 3x minus iy. So you can see that the term has modified. Instead of 3x minus y, it has 3x minus iy. So so you can expect that this will not work, and it doesn't work. So what, so if the function has this form 3x minus y, it will work, or 3x plus y, you can try that. But the thing is, this form should be there, and this doesn't fit, the d equation doesn't fit that form. Okay, so these two equations, they will work. Okay, so these two equations satisfy the PD. Okay, I hope this is clear. So we'll go to the next problem. Okay, so the next question is the solution of the initial value problem. So this equation is given, differential equation, and initial state is given, or you can say the boundary condition is given, y1 is equal to 0 each. So okay, so first of all we'll write the x y prime is equal to y plus 3x raised to 4 cos square y by x. Okay, so we'll deal with the initial value at the end. So you can see the hint here, which is y by x. So somehow we have to simplify this equation. So what we will write is z is equal to y by x, and so this y prime is nothing but dy by dx. So we will differentiate this equation with respect to x. Okay, so if you differentiate, it will be 1 upon x dy by dx, and let's say we differentiate 1 upon x, which will be minus 1 upon x square, and let's say we are keeping y as it is, and yeah, that's all. Okay, so what we are solving this equation. You can see that x y derivative is there. So if we multiply this both side by x square, let's say, so what we'll get is x square dz by dx is equal to x dy by dx minus y. Okay, so what we can do is we can take this y on this side, so which is nothing but this x square dz by dx. So we can write dx y prime minus y is equal to 3x raised to 4 cos square y by x, and this whole term is nothing but here. Okay, so x square dz by dx is equal to 3x raised to 4 cos square y by x. Okay, so this y by x we will write z. Okay, so dz by let's say we'll separate the variable. which will be cos square z, and 3x square dx. Okay, so this is nothing but sec z square dz is equal to 3x square dx, and so on integrating this will be tan of z is equal to this will be x cube by 3, so 3 get cancelled, it will be x cube plus constant. Okay, so we have the solution. What we'll use is this initial condition that is given, y at x is equal to 1 is 0. Okay, so y at x is equal to 1 is equal to 0, so that is given, so we'll substitute here. So 1, okay, so let's write it properly because we have z in the equation. So tan of y by x is equal to x cube plus c. Okay, so if y is equal to 0, so what we will get is, okay, tan of y by x is equal to x cube plus c. Y is equal to 0 at x is equal to 1, so we'll write 1 plus c, and tan of 0, which will be 0 is equal to 1 plus c, and that gives c is equal to minus 1. So this is the c value. If we substitute that into this equation, we'll get tan of y by x is equal to x cube minus 1, and we can write tan inverse of x cube minus 1, and this will be y by x, so let's say multiply this x on this side. So this is the solution. Okay, so this one also was straightforward. So y equal to x tan inverse x cube minus 1. Okay, so the first solution matches, so this is the correct answer. Okay, I hope this is clear. So we'll go to the next question. So you can see that a lot of questions which are having the same thing, which is what is the wave speed. So you can don't miss this question in the final exam. So this is the wave equation, and you can see that c square is nothing but 9, so c is equal to 3. So this is the equation. So the equation in general is dou square u by dou t square is equal to c square dou square u by dou x square, and it doesn't matter whether you write in 3D or 2D, because you are not solving actually for this, so you are just finding out the wave speed. So that is just related to this term, and which is nothing but, you can see that it is 1 upon c square, so c square is 9 and c is equal to 3. So this is the correct answer. Okay, okay, so the next question is, which of the following equations are of time marching time? So you can see that imagine that time marching solutions are where they will be evolving with time, and you can imagine this is the wave equation, let's say. So you can see that this wave will go, let's say, on the right, and you have to, this will be like time marching solution you have to find out. So you can see that where this wave will go, at what direction it is going, and at different time instant it will have different locations. So this is t0, at some other instant it might have moved forward, which is t1. So this is this kind of equations, they are related to time marching solution. But let's say you have some let's say some region, let's say this one is at t1, this is, let's say, some, let's say, t dot condition is given here, let's say t dot at l, or you can say the spatial derivative of t with respect to, or flux is given on this side, so flux is also given at this line, this side, left side, then this is, let's say, t0. So if this is given, you can see that this will have that the solution inside will get fixed, or it will reach to the steady state solution, and that's all you are supposed to determine. So some situation, it depends what equation you are solving. So if you are interested in steady state, that time it doesn't matter that whether this is time evolving or time marching solution. You are directly interested in the final solution, or how the steady state solution are. So I will write the this general form for this. So if you have some partial differential equation, let's say dou square, let's say u by dou x square plus b dou x dou y plus c dou square u by dou y square, then d dou u by dou x, e dou u by dou y plus f is equal to 0. Some partial, this is general partial differential equation. So in that case, there are different types. Let's say first is, we'll say, hyperbolic. So hyperbolic will have b square minus 4ac greater than 0. So you can see that this term we are not using to find the nature of this second order partial differential equation. We are just taking these three terms and their coefficients. So hyperbolic, then parabolic. So in that case, b square minus 4ac will be 0, and elliptic, in this case b square minus 4ac will be 0, and you can think of whatever we are interested here. This is discriminant, and if you see minus b plus minus square root of b square minus 4ac by, let's say, 2a, and let's say these terms are, we are not interested, so let's say they are absent itself. So if we see this equation, you can see, consider this is related to, somewhat related to, let's say, characteristic wave speed. So we'll see like the wave equation, and we can see that this is actually the wave speed, and it will come out to be plus c minus c. So you can see that if the wave is there, the wave can go this direction, let's say at speed c, or it can go in this direction minus c. Like the minus c is like this, does denote the direction. Okay, so this is both possible cases, and you can see that this is actually the case where you have this wave speed, and this is related to the characteristic motion, or you can say this is related to the time evolving solution. So in this case, you can see this wave speed exists, and then it is related to the wave motion, and then time evolving solution. So we'll see that for three equations, how this like we'll see these three examples of hyperbolic. So we'll see example for each of this: hyperbolic, parabolic, and elliptic. So let's say we have heat conduction equation. So heat conduction equation, you can see dou u by dou t is equal to, let's say, c square. C square is need not to be the speed, but it's just some constant. So what if we find out b square minus 4ac? So if b square minus 4ac, so you can see this c square is nothing but a. C square is nothing but a. Okay, so we write a. So let's say 4 into this is c square, and so c is corresponds to the coefficient of second derivative with respect to y, and there is no term, so it is nothing but 0. And b corresponds to this partial derivative with respect to x and y, so that term also is absent in this equation, so that is also 0. So you can see this whole term is 0, so that corresponds to this parabolic equation. And you can see that this is the heat conduction equation, and let's say you have this x is equal to 0 and x is equal to L, and let's say this temperature at this is T1 and at this end is T2, and let's say T1 is greater than T2. You can see that there will be time evolution where, let's say, suddenly you have initial some profile is there. So this is the T1 and this is some profile you have given initially, so finally it will try to adjust to this steady state solution, but till then it will be time evolving. And you can see that this is corresponds to 0, so this is time marching is exist in this, so time evolving situation is there, but this term is 0. So you can see, consider this as at the boundary where the parabolic and hyperbolic are getting separated, but still you can see that for parabolic equation there is time marching, or you can see that even this term is 0, this term can be present, which is b. Actually it is absent here, the b term is absent, but still this whole term you can see that there will be some way the time evolution has been incorporated because of the other terms in this equation, and it is parabolic equation. And then we'll see one example for hyperbolic, where which is just nothing but the wave equation itself. So dou square u by dou t square is equal to c square dou square u by dou t square. Okay, so we'll write a is equal to let's say we don't have, so here we, instead of y we have t, and a means c square, b is equal to 0, and c is equal to, so let's say we take this term on this side, which is minus 1, so this coefficient so c square dou square u by dou x square minus dou square u by dou t square. Okay, so this is the equation, and a is equal to c square and c is equal to minus 1, so these are capital C. So if we write b square minus 4ac, b square is 0, 4 into a is c square, and capital C is minus 1, which is nothing but 4c square. You can see this is greater than 0, and actually if you go to this wave speed equation, you can see this minus b plus minus square root of b square minus 4ac divided by 2a. What will be there is, let's say, minus b is 0 plus minus let's say square root of 4c square divided by 2c square. Okay, so what will be the case, 2c divided by 2c square, which is nothing but 1 upon c. So you can see that this is somehow related to the speed at which things move, and somehow related to the wave at the speed at which the information propagates, or this wave propagates. So this is so you can see that this term is related to the propagation speed of wave, and if this term inside is 0, it means that there is only one direction at which it is going, the conduction or whatever is going in one direction. If this square root term is like the term inside the square root is positive, which is this, so it will have two roots, and two roots means two direction the flow will happen of the information or whatever variable we are considering. And if this term is imaginary, it means that the flow will, so you can think of that we already have the if it is real, it means actually it corresponds to the propagation, but if it is imaginary, it doesn't corresponds to the propagation. So that is that's why it is like there is no proper direction of propagation, and that's what it is called as elliptic. Okay, so we'll see the next example of Laplace equation. So let's say dou square u by dou x square plus dou square u by dou y square. So in this case a is equal to 1 and b is equal to 1. So if we write b square minus 4ac, it will be 1 minus 4. A is 1 and c is 1. In that case it will be minus 3, which is less than 0. So in that case so this is actually corresponds to the steady solution you can think of, and there is no proper direction of propagation, or the information propagates from all the directions you can think of. So this solution at this location will be dependent on the what neighboring points are, or so that way. So in that case like the information will be coming to this point from all these directions. So and if you see the wave, so you can see that let's say there is sine wave. So in that case you can see this is going in particular direction. So at this point the information is coming from this backside direction, or there is proper direction to of the motion. So let's say this corresponds to the plus c wave motion. So yeah, so that's, so this actually corresponds to, because it is the discriminant is negative, it is corresponds to the elliptic. This this is the wave equation, and this is hyperbolic, and we saw the heat conduction equation, which is parabolic. Okay, so that's all I have, but we'll solve one equation. I think professor already talked this, might have taken this equation, but we'll just we'll solve it for just for the practice. So let's say we have this equation dou square u by dou x square is equal to 16 dou u by dou y. So we want to solve this equation. So what we will do is we'll use the so this is, you can see that we have two coordinate x and y, and we'll assume that the solution in these two coordinates are independent. So we'll say that this is nothing but capital X, which just depend upon x, and that is the solution on y, which is just depend upon y. So this independence we are assuming here, and if we use this independence, we'll see whether the equation gets simplified or not, and if it gets, we can solve it. Okay, so we will substitute this, and if we differentiate it twice, so it will be x double dash into y is equal to 16 dou u by dou y, which is y dash. Okay, so we can see that this is already close to our variable separable form. So x double prime, okay, sorry, this I missed x. So x is equal to let's take 16 also here, so it will be y prime upon y. Okay, so this left hand side is just the function of x, so this is function of x, and the right hand side is a function of y. So this is small x and small y, because we are saying that capital X is function of x and capital Y is function of small y. So these are independent, so it doesn't matter what x location we are taking or what y location we are taking, they are supposed to match. So if that is the case, this must be some constant. So this must be some constant, because for all the y's this side can side should match with the whatever x values is given. So if that is the case, it means that they are not changing, changing, so it must be constant. Okay, so what all possible situations are there, we'll find out, and we'll see what solution we'll get. Okay, so this constant can be, let's say, minus x square, which is less than 0. So constant is just less than 0, or it can be equal to 0, which is nothing but, let's say, 0, and it can be positive x square, which is greater than 0. So this constant can take three values. These are all real values, and these real values can be less than 0, 0, or greater than 0. So we'll solve for all these three values for the constant, and we'll see what solution we get. So x double prime by 16x is equal to y prime by y, and let's try minus k square. So we'll say this is case 1. Okay, so anyway they are independent, so we'll write x double prime minus, okay, is equal to minus k square 16x, and for y we can write y prime is equal to minus k square y. Okay, and if we solve, let's say, x double prime plus k square 16x is equal to 0, and y prime plus k square y equal to 0. Okay, actually we could have solved it. Okay, now we'll solve it. So let's say this is how we solve the general linear differential equation. So for this the roots will be minus, so here there is plus sign at the center, so it will be imaginary roots will be there. Okay, I think yeah, so it will be d square plus 16k square equal to 0. We'll solve, or you can say, instead of d square, if you are interested, you can write lambda square, which is characteristic equation. Okay, so d is equal to plus minus I 4k. Okay, so what we'll get is x is equal to c1 e raised to I 4kx plus c2 e raised to minus I 4kx. Okay, and these two terms we can write in terms of sine and cos. So eventually we'll get a1 into cos 4kx plus b1 sine 4kx. Okay, and so this one we got the solution for x. You can see this is kind of sinusoidal, and the next thing is, if we solve this, you can see that this equation has just one root, which is k, and or you can say minus k. So this one will be y is equal to let's say c1 c2 we have used with c3 e raised to minus k square y. Okay, so here itself we can directly solve this for y, and our solution u is equal to x into y. So finally if we multiply these two, so we will say a, so a is nothing but a1 into c3 cos 4kx plus b sin 4kx into a raised to minus k square y. Okay, so this is the solution for case 1. So what case 1 we are considering is this is less than 0, so k square is less, so this the ratio we are saying this is less than 0. Okay, so the case 2 we will see where the constant that we are considering is equal to 0. So x double prime 16x is equal to okay, let's say y prime y is equal to 0. So in that case what we'll get is x double prime is equal to 0 and y prime equal to 0. So if this is the case, x is equal to let's say c1x plus c2 and y is equal to c3. And if we multiply for the solution u, which is x into y, so this is small x. Okay, so the solution will be c1x plus c2 into y, which is c3, and finally let's say it is ax plus b. Okay, so this is the case, the solution for the case 2, and we already considered that this constant, this was the case 1, this case 2 also we considered, and the case 3 will be k square, which is greater than 0. So in the case 3 what we will consider is constant is equal to k square, which is greater than 0. Okay, so okay, we have already simplified it, which is x double prime x 16x is equal to y prime divided by y is equal to k square. Okay, so we'll write this two term at a time, and which is similar to what we did before, which will be k square, and y prime y is equal to k square. So x double prime minus 16k square x is equal to 0, and y prime is equal to k square y. So you can, this is nothing but capital Y by dy small y, and k square y. So this one what you will get is y is equal to e raised to k square y, and c, let's say c3, and here we will get c1 c2. So let's find out. So in this case the roots or eigenvalues, or you can say the roots of the characteristic equation will be plus 4k minus 4k, and if you write the solution, the x will be c1 e raised to 4kx plus c2 e raised to minus 4kx, and then we'll take the multiplication. So the solution, and one more simplification if you want you can do is this one, two terms can be written as sine hyperbolic x and cos hyperbolic of this exponent. So we will write that, let's say take cos first, cos hyperbolic, it will be cos hyperbolic 4 cos hyperbolic 4kx plus b1, let's say sine hyperbolic 4kx. Okay, so we will multiply this 2 So u is equal to x into y, and x we got as a1 cos hyperbolic 4kx plus b sin hyperbolic 4kx, and y is c3 e raised to k square y. Okay, so after taking the c inside, finally it will be a cos hyperbolic 4kx plus b sin hyperbolic 4kx, and outside e raised to k square y. Okay, so these are the three cases. These were the three cases possible for this, and we saw how to find out the solution for this given equation. And this was like similar to the heat conduction equation. So instead of y, if there is a time, you can think of this as a this equation for the this whatever we saw here. So this is the heat conduction equation. So similarly it was. Okay, so this equation, I think and yeah, do you have any doubts in this?
No, sir, not for now.
Okay, yeah, if no doubts, we can stop for today.